Bismillahirrahmanirrahim. Now, today we will discuss about rapidly varied flow. This is lecture number 9 of the course Hydraulics. Now, in the previous lecture, we studied about the gradually varied flow problems. So, in that case, we developed the energy equation that we can write for the gradually varied flow problems. Then we discuss in detail the different water surface profiles for prismatic channels. Towards the end of the lecture, we discuss how we will computation of water surface profiles for gradually varied flow. So as I said that there are different methods, but the one that we are going to study in detail, that is the direct step method. It is also known as step-by-step method or stepwise method as written in your textbook. Step-by-step method. Now this is called direct step method because the solution is direct, no trial and error. And essentially in this method, given two depths, mean depth of water, how far apart. Clear? So if we have two depths of water, for example, if I could draw it here, so let's say we have two depths, let it be a increasing profile. So we have this smooth line here. So let's say this is 4 feet and this is 3 feet. Now we have this depth of water, you see it is variable between 3 and 4 feet, so that's why it is a varied flow, non-uniform flow. So in this case, if we want to know that these two depths are how much apart, and this we designated by delta x. So this is what we answer in this method. So since the depths are known, the cross section of the channel will be prismatic, clear. It is not going to change between 3 and 4. So that's why the solution is direct, no trial and error, and we can easily calculate this delta x. We already developed the equation for this. So essentially in this direct step method, we answer that for any given two depths, how far they are apart. Now, we also studied about the procedure how to use this method to compute the water surface profiles, because in this method you calculate these distances and these depths, and at these distances when we plot these depths, for example, this is just a very simplified example. So in that case what we have is that we have, let's say this is 4 feet, then 3.9 feet. At this much distance we have to calculate, then 3.8 feet, then 3.7, just in an example, 3.6, 3.5, then 4, then 3, 2, and 1. So you can see that when we join them we get this water surface profile. So it can be increasing one or it can be a decreasing one. Clear? So that's why we say computation of water surface profiles. Now in this method, it considers the difference in specific energy at two locations. Why the difference in specific energy? Because you can see that the depth is variable. If the depth is the same, we have uniform flow. So in case of uniform flow, we studied that the specific energy remains constant, the depth plus velocity, because the depth is the same at all sections. Consequently, velocity is the same because we have steady flow. So that's why in case of uniform flow, the specific energy is constant along the channel section. Clear? The total energy that will decrease in the direction of flow if we consider the head loss. So this is already understood. But remember, in case of uniform flow, the specific energy will remain constant, clear? And it can increase or decrease when we have non-uniform flow. So in varied flow, which we are going to study right now, so in this case, the depth is changing. So consequently, the velocity is not the same at all sections. So that's why there will be change in the specific energy. So because there is change in the specific energy, we have this non-uniform flow. And relative to channel slope and energy grade line or energy line slope at midpoint between two sections. Because in the basic equation that we studied, if you remember, what was the equation? The equation was that this delta x, which is equal to E1 minus E2 divided by S minus S naught. This S is the slope of the energy line and S naught is the channel bed slope. Now in this equation, we can calculate everything. This energy slope of the energy line or energy gradient, this is actually calculated from the Manning's formula. This is calculated from the Manning's formula. So what was the equation for this? That we have N, Manning's roughness coefficient, then we have the velocity V bar divided by, depend on the system of units. If we have British gravitational system, so this is 1.486. This is 1.486 RH bar. This is the hydraulic radius RH bar, and this power 2 by 3. Power 2 by 3, and this whole square. This whole square. Now in this equation, if you remember, this V bar, this is actually equal to V1 plus V2 divided by 2. And this RH bar, this is equal to RH1, that is the hydraulic radius at section 1, plus we have RH2, that is the hydraulic radius at section 2 divided by 2. So it means we are averaging the conditions between the two sections considered, clear? And essentially what we are doing is that this difference of depth, you can see here that there is difference of depth between the two sections that we have considered. So the smaller the delta x, the smaller will be the difference of depth between the two sections, because this Manning's formula, it is applicable for uniform flow, in which case we are assuming that the depth is the same at all sections. So the smaller this difference between the two sections, the more accurate we will get the results. So that's why it is written here that relative to the channel slope and energy grade line slope at midpoint between two sections, because you are averaging the conditions, clear? So what was the steps that we have to follow? We will be given the depth range in this method, the direct step method. So we have to divide the depth range of interest into small increments usually equal. So we will divide the depth range into small increments, and we already learned in the previous lecture that the smaller the increments, the greater will be the accuracy of the results. But one disadvantage is computational time will increase. So for example, we have a depth here, whatever you call it, let's say y2, and then another depth here, and let's say it is a rising profile. It can be a falling profile, that is drawdown curve. So let's say this is y1. Essentially what we have to do is that we will divide this depth range into different sections, and the division of the depth range, that will depend on the purpose of the problem, that how much accuracy is desired. So what we do is that we will divide this into increments that are usually equal. So small increments define the reaches whose lengths can be found by delta x is equal to E1 minus E2 divided by S minus S naught. This is what I have written here. And in this equation, this S can be calculated using the Manning's formula in the British gravitational units and in the SI units. You can also use the Chezy formula, clear? But you have to consider, you see that the value of N, the Manning's roughness coefficient. So if the Chezy C is known, then we can also apply the Chezy formula. Now in this case, we have to calculate this discretization that we do. It means that for the given depths that we divide into the different small increments. So this discretization process must begin from a section where y is known. So you have to start from a section where y is known, because we have to calculate delta x, and if y is known, so unknown also, then we cannot solve the problem, clear? So at a time one should be unknown. So they say that this, let's say you start from y2 and then you proceed in upward direction, or in case of drawdown curve, if we have a drawdown curve like this, so what we can do is that either you start from here, proceed in this direction, or you can start from here and proceed in the upward direction. So either a rising curve or a falling curve, which we call it as drawdown curve, you have to start from a point where the depth is known. And as we studied about the control section, because on the control section the depth discharge relationship is definite, so we can start the calculations from a control section. Or if we do not have a control section, then we can go to the field and measure the depth of water at any section, and then based on that we can proceed for the calculations. Now in this case, what essentially we do is that you have to calculate for each of increment this delta x. So let's say here we have this delta x1, then for the next it will be delta x2, this will be delta x2, and so on. So the final will be, let's say we are proceeding in the upward direction, so the final will be delta x n. So now you want to calculate the total distance. So then the total distance, that will be equal to delta x, that will be equal to summation of delta xi, where I is equal to 1 up to n. Now in this case, because we can proceed in this direction, or we can also proceed in this direction, means that we can proceed upstream of a point of a section, or we can proceed downstream of a point or a section. So that's why this delta x can be plus and can be minus. So if we get a negative sign here, then it does not mean that we have error in the calculations. So if the resulting value of delta x is negative, then this means that the section 2 is upstream of section 1. It means that if delta x you get as minus, then it would mean that this is your section 2 and this is your section 1. It means that we proceeded in the upstream direction. So the answer will not be correct if we, it doesn't mean that if we get negative answer, the answer will be incorrect. So remember, we can get a plus and a minus sign. The plus minus will only indicate that section 2 is upstream or downstream of section 1. So this is the direct step method. You can see the solution is direct. We do not have a trial and error procedure. Now, what can happen is that this method, this is only applicable to prismatic channels. Remember, this is applicable to prismatic channels. Now, I will just briefly explain if we have natural streams, for example, rivers, then in that case, the channel cross section is no longer prismatic. So then we cannot apply this method. Why? Because the parameters are changing from section to section. Clear? So in that case, let me just briefly explain how we solve those problems, although they are not explained in detail in your textbook. Clear? So just let us see that in the direct step method that we just discussed. So this is direct step method. Now in this method, what we essentially do is that we are given two depths and how far apart that we have to calculate. For example, if we have a rising profile, so let's say we have this is y1 and this is y2. So what we did is that we have to calculate this delta x. Clear? So this delta x, that is essentially unknown. We will solve a problem after this, so you will see how we apply this direct step method. So now this how we do it, and then for each of the section we calculate, and then those points we can plot and we can get this profile by joining all the points. So we will be able to plot this profile either increasing or decreasing in the direction of flow. Now the other method, for example, if we have in case of natural stream, let's say we have rivers, or let me write down here, when we have natural stream, because here the channel must be prismatic. So when we have natural stream, it is no longer prismatic. So the method that we apply, actually it is just briefly explained in a few lines in the textbook, but not in detail. So that is known as the standard step method. For this, the method that we are using is known as the standard step method. Now in this standard step method, what we do is that the same section, it is for natural stream, clear, the same section, we start from a depth which is a control section, clear, let's say this is here y2, and this is assumed, this delta x, this is assumed, means that this is given. And we say that this is y2 which is given, the next depth y1, it is how much, what is this y1 for the given delta x. So now you can see that this y1 becomes unknown. So in this equation here we cannot directly determine. the factors here, because in the hydraulic radius we have the flow area and we have the wetted perimeter that we average. So that's why if the depth is unknown, then we have unknown quantities in the numerator and in the denominator. So essentially it becomes a trial and error solution. Clear? Now for a natural stream, the solution is not direct because the form and dimensions of a cross section cannot be assumed, and then the distance to its location computed like we did in the direct step method. We cannot assume the dimensions and the distance can be computed to that. This cannot be done here. Clear? Why? As there are various slopes and cross sections at different distances upstream, so that's why we must assume the value of delta x, and then we can compute the depth of stream at this section by trial and error. So the solution here will be a trial and error solution. This will be a trial and error solution. So it means the solution is now complex. Trial and error solution. So remember, this standard step method, it is applicable to both prismatic and non-prismatic channels. Now, if you have heard or studied about, there is a software which is known as HECRAS. Now, when we are analyzing the river analysis systems, so there is a commonly free software. This is in public domain. So this is known as HECRAS. This HECRAS, it is developed by US Army Corps of Engineers. This is known as Hydrologic Engineering Center River Analysis System. HECRAS, Hydrological Engineering Center River Analysis System. So we commonly call it as HECRAS. Now this, because this HEC, which is Hydrologic Engineering Center of the US Army Corps of Engineers, they develop these software and they develop other softwares also. It is one of them. So this HECRAS river analysis system, it actually incorporates this standard step method. So whether we have prismatic channels or non-prismatic channels, so we can use this software. This is a software. It is freely available. It is in the public domain. You can download. So this incorporates this standard step method. So these are just the two methods, but as I explained before that there are different methods for computation of gradually varied flow profiles. For example, we have the graphical integration method of direct integration, and this direct step method and the standard step method. So there are different methods. If you are interested, you can study about them in detail from the specialized book on open channel hydraulics, such as this Open Channel Hydraulics by Wenty Chow, which is available online. So you can study about all the methods in detail. Clear? Okay, now let us try to solve a problem to see that how we apply these concepts that we learn in today's lecture and in the previous lecture to solve the problems. Clear? Now this is problem 10.17.7 from the textbook. We have a laboratory flume. The Manning's roughness coefficient, Manning's N, is given, and the flume is 10 inches wide. So we have to keep the units consistent in the problem to avoid any mistake. It is set on a slope of this much with a measured flow of 0.1516 CFS, cubic foot per second. Now the depth is observed to vary between 0.361 and 0.366 feet. So now the depth is changing and it varies between this 0.361 and 0.366 feet. So it means that this is a gradually varied flow problem, clear? Because the depth is changing, no longer uniform flow. Now we have to answer this question is that classify the water surface profile. What type of profile is this? As if you remember, we studied that in case of gradually varied flows for prismatic channels, how many different profiles, water surface profiles? How many of them? 12. 12 water surface profiles that we studied in the previous lecture. So we have 12 water surface profiles. So now among them we have to determine that for these given conditions, what type of profile is there. And remember, these are for prismatic channels. Clear? We have 12 profiles for gradually varied flow. If we have non-prismatic channels, then there can be 20 typical profiles which are given. You study open channel hydraulics by Venti Chow. Now we have to classify the water surface profile and show all the necessary calculations, and we have to sketch the profile. We have to draw the profile. Clear? So now the problem is given in the British gravitational system. So accordingly, we will use the Manning's formula. So let us try to solve this problem here. Now the Manning's formula for the discharge. Now remember, B is given. This is the width of the channel. It is a rectangular channel. Clear? The width is 10 inches wide. So we have this is 10 inches. Now keep the units consistent to avoid any mistake. So this will be equal to 0.833 feet. You divide by 12. 0.833 feet. Now we are given the Manning's N. The slope is given. This is S naught. Clear? And the depth range is given. Now how we have to determine that what type of profile is this? So it means that first we have to determine, because if you remember, we studied that there are different types of channels or slopes. We studied that we can have a mild slope, we can have a steep slope, we can have a critical slope, horizontal slope, and adverse slope. So now you can see that in this case it is set on a slope of this much. So now we do not have the horizontal slope, we do not have the adverse slope, because in that case the S will be negative, that is increasing in the direction of flow. And critical slope, when we have the slope of the bed of the channel that is equal to SC, the critical slope that we can calculate. So now let us see that what type of slope is there first. So how to determine that? The depth range is given. We actually need to compare. If you remember, in the types of profiles, there were the channel vertical section of the channel that was divided into 3 types or 3 regions or 3 zones. So type 1, type 2, and type 3. Clear? So first we need to determine the normal depth for this given discharge and also the critical depth. And then we can compare the given depth of flows with the normal depth and critical depth, and we can get the idea that what type of channel is this. And then once we can determine that it is a mild channel or it is a steep channel or it is a critical channel, then we can go for the type, corresponding type of that channel. So that's why you have to first calculate the normal depth and the critical depth. So we will get the idea from there. So now to determine the normal depth, we write down the Manning's formula. So the Manning's formula in the British gravitation system is 1.486. Says 1.486 divided by n into area, because we have discharge, so area into the hydraulic radius RH 2 by 3, and we have this S naught 1 by 2. Now in this case we have to calculate Y naught. So area will be equal to B times Y naught, which is the normal depth, that is the depth corresponding to uniform flow. So that will be equal to B times Y naught, and B is already 0.833, so this will be equal to 0.833 times Y naught. And then you have to calculate the hydraulic radius. So the hydraulic radius, that will be equal to 0.833 times, that is area divided by the wetted perimeter. The hydraulic radius is area divided, flow area divided by the wetted perimeter. So area is 0.833 Y naught, and this P, because we have rectangular channel, so it will be equal to 0.833, that is the width of the channel, times plus 2 times the depth, which is Y naught. So now this you have to put here. So you can see that Y naught is in the numerator and in the denominator. So this will be equal to 0.833 times Y naught divided by 0.833 plus 2 times Y naught. Now we have to put the values in the Manning's formula. The discharge is given. How much is the discharge? 0.1516 CFS. So you can put the discharge 0.1516, and on the right hand side we have this formula, that is 1.486 divided by n. N is given. You can put the values. You can put the area 0.833 times Y naught, and then you can put the hydraulic radius, which is 2 by 3, and we have this S naught, it is given. This is power 1 by 2. Now because Y naught is in the numerator and in the denominator here, so that's why it is a trial and error solution. So that's why by trial and error, as you have already done this so far, by trial and error, now you can see that the uniform flow problems are just a step now in these problems. By trial and error, so we will calculate this Y naught. This will be equal to 0.279 feet. 0.279 feet. Now the depth range is given, and we are given Y naught. So you can see here that this depth range, which is given in the laboratory flume, that is above Y naught. Next we see that what is the value of the critical depth. So now in the critical depth, so we can easily use this formula. because we have rectangular channel, YC is equal to Q square divided by G, and this is whole power 1 by 3. Now you put the values, everything is known. The discharge is given, divided by the width, you will get the small q. This small q, that is equal to the total discharge divided by the width of the channel. So now when you put the values, so we get YC, that will be equal to 0.1, 0.1009 feet, 0.1 feet. So now you can see that what was the value of y naught? Y naught is equal to 0.279, 0.279 feet. So now you can see that it is greater than YC. So it is greater than YC here. What is the value of YC? 0.1009 feet. So what it means? This basically means that the slope is mild. What it means? It means that the slope is mild. It means for the given condition, we have mild slope. Y naught is greater than YC. Now in this case, because the slope is mild, so you already know that for the mild slope, we denote the slope by M. We denote the slope by M. Now in case of mild slope, there are three types possible. We have M1, M2 and M3, as we studied in the previous lecture. So now we know that the slope is mild, because what is the question? It is asked that classify the water surface profile. What type of profile is this? So now so far what we have done is that the slope, the channel is mild. The slope is mild. So now this M1 is possible, M2 is possible, M3 is possible. Clear? So we compare the depth range which is given. This is your Y. This is the depth range which is given to us. So now we compare this depth range with the normal depth and with the critical depth. So you can see that this Y range, this given, you can see here, this given Y range, it is greater than Y naught, because this is 0.361 and 0.366 and Y naught is 0.279. It means that it is above Y naught and Y naught is greater than YC. So we already studied that in case of M1 profile, this M1 profile here, when we use the type 1, it means that the depth in the channel, the depth of flow, that is above the two. Which two? The normal depth and the critical depth. If we have, for example, this is the channel and it is a mild channel, clear, it is mild. So we already discussed that the three types of profile that can develop. We have this is, let us assume, the critical depth. So we have YC line. Then we have, let us say that this is your normal depth line. So if the depth of flow is here, then it is type 1, above the two. When it is between the two, we call it as type 2. And if it is below the 2 means y0 and yc, we call this as type 3. So now you can see here that the depth range which is given in this problem, it is above the 2. Clear? So it means that the depth is somewhere here. So that's why it is not M2 profile, it is not M3 profile, it is M1 profile. So first we determine that what type of slope is this, and then on the same slope what type of profile is this. So from here what we get is that it is M1 profile, M with a subscript 1 profile. Now show all the calculations as we already showed, and the next question is sketch the profile. So if we want to sketch the profile, let's say this is the mild slope here. This is the mild slope. We can sketch the critical depth. So let's say this is the critical depth. Then we have to sketch the normal depth. Let's say it is a solid line. So this is the normal depth line. This is the critical depth line because we have mild slope. So the normal depth is above the critical depth. And let me use another color. So we have to plot the depth variation 0.361 and 0.366. So now it will be a down profile. Can we draw it like this? No. Why? Because we already learned that M1 is a rising profile. Because we already studied in the previous lecture that for M1 profile, the dy by dx was positive. So it means that it is a rising profile. So that's why you cannot show it that it can vary from 0.366 to 0.361. No, this is incorrect. So M1, if it is M1 profile, it will be a rising profile. And this is how we can plot a smooth profile gradually increasing. So the depth here can be represented as 0.361, can be written as 0.361 foot, and at the other section it varies 0.366 feet. So this is essentially M1 profile. So this is how we solve the problem. Clear? Now next we try to solve another problem. So this is problem 10.9 from the textbook. Now in this problem, at a certain section in a very smooth rectangular channel, which is 6 feet wide, the depth is 3 feet. When the flow rate is 160 CFS, now discharge is given. Compute the distance to the section where the depth is 3.2 feet. S0 is this much, the channel bed slope, and the Manning's N is given. So now what we have to do is that let us try to solve this problem we have to draw a table because there are many calculations in this. So we are given that the channel width, it is a rectangular channel, so calculations are little easy. So we have 6 feet. This is the width of the channel which is given, and Manning's N S naught are written here, and the total discharge that is given is 160 CFS, 160 cubic foot per second CFS. Now what we have to do is that we have to calculate actually delta X. This is what we have to calculate, and it is given that the depth is 3 feet, and compute this delta X to the section where the depth is 3.2 feet. Clear? So in this equation delta X that we will calculate, we will use this equation that we developed. Delta X is equal to E1 minus E2 divided by S minus S naught. S minus S naught. So it means we have to calculate the values of the numerator and the denominator. Now in this case we can solve this problem in one step, because the two depths are given and we can easily calculate the specific energy at the two section, and the S naught which is given, and this S which is the slope of the energy line by the Manning's equation as we discussed. But as we learn that if we want to increase the accuracy of calculating this delta X, we can divide the section into small increments. So that will increase the accuracy of the results. So what we do is that we can now, this S can be calculated by using this Manning's formula, that will be equal to N into V bar, because the problem is in British gravitational system. So that's why we will write down here 1.486 into RH bar average. This is power 2 by 3, and this is whole square. Now in this case you see that we have to calculate the average of the velocity and the average of the hydraulic radius at the two sections. So that's why we can draw a table to simplify the calculations. For example, first will be the depth, so this will be in feet. Then next we will have the area. So now the width is fixed, only the depth is changing, so that's why we can write down this as 6 times y, and this will be in square feet. Next we have to, because in this we have to calculate the hydraulic radius, so next we have to estimate the value of the wetted perimeter, and this wetted perimeter, this will be equal to 6 the width which is fixed, this is not going to change, plus 2 times the depth, so only the y will change. For the y value only this will change, and here the units will be feet. And then from here, because we have the flow area and we have the wetted perimeter, so from here we can calculate the hydraulic radius. So the hydraulic radius will be simply equal to A by P, and it has the units of length. Now after this we can also calculate, because we have the flow area and we have the discharge which is given, so we can calculate the velocity, because you can see here the average velocity we have to calculate. So we can calculate the velocity, and that will be simply equal to the discharge divided by the area A. And because it is velocity, so the units will be FPS, foot per second. And once we have the velocity, we can calculate the velocity head. So the velocity head, that will be equal to v square divided by 2g, because we have to estimate E1 and E2. So that is the depth of flow plus the velocity head. This E1, as we already know, that this will be equal to the depth, which we already in the first column we will consider, and plus we will need to calculate this v square by 2g, plus we have the velocity head. This is actually your specific energy. So keeping the units consistent, take care of the value of g to avoid any mistake. Since this is a velocity head, so it has the units of feet. This we will calculate here, and this depth plus the velocity head, we will be able to calculate the specific energy. Clear? Which I already write down here. This is the formula. So this we will calculate, and it is the units of feet. So up to here we do calculation, then the table will continue after this to arrive at the average values. So what we do is that first we are given this 3 feet here. You can see that the depth here is 3 feet. So for the 3 feet we do the calculations. So we have this 3. Now area, flow area, 6 multiplied by 3, this will be 18. You can calculate now the wetted perimeter, so that will be equal to 12. The hydraulic radius, that will be area divided by the wetted perimeter, so this is equal to 1.5. and the velocity discharge divided by the flow area, so this will be equal to 8.889. 8.889, and then the velocity head, that will be equal to v square divided by 2g. So take care of the g value. So this we will be calculated as 1.2269, and this specific energy, it will be equal to this 1.2269 plus 3, as given by this formula here, this equation. So this will be equal to 4.2269. 4.2269. So these are now calculations for this 3 feet. Clear? Now we can proceed, because we have to discretize the distance between this. So now next what we do is that from 3 to 3.2 feet. So that's why next we can assume, let's say 3.1. We can directly take this 3.2, but in that case we consider only one section, that is between 3 and 3.2. So as I said before, if we want to increase the accuracy, we can consider the smaller increments. This will increase the accuracy of results, but the disadvantage will be that the computational time will increase. So 3.1, now you multiply this with 6 to calculate this area A. So this will be equal to 18.6. Then this wetted perimeter, this will be equal to 12.2. The hydraulic radius, that will be equal to 1.525. 1.525. This velocity will be equal to 8.602. 8.602. Velocity head v square by 2g. that will be equal to 1.1490, and then this velocity head plus the depth of flow, this will give us the specific energy. So this will be equal to 4.2490. And next we consider this 3.2. So this will be equal to 3.2. This is what we are asked, that we calculate the distance between this 3 and 3.2. So this will be equal to 19.2, and the wetted perimeter, this will be equal to 12.4. This will be equal to 1.548. This is equal to the velocity 8.333, and then the velocity head 1.0782, and the specific energy will be depth of flow plus the velocity head, that will be equal to 4.2782. Now what we have to do, now we have to do the calculations for the rest of this table. Will now continue for the midpoint now. Why? Because we have to, in order to estimate the value of delta x, we need now the difference of the E1 and E2. So this is your E1, this is E2, the difference we need to calculate. So what we have to do is that we have to now calculate E1. That table now continues. So we have E1 minus E2. So it is just the difference of the two energies. So that's why this is in feet. And after this, we have to calculate V bar, the average velocity. So again, the units are foot per second. And next we have to calculate your RH, the hydraulic radius, RH bar, average of the two. Again, the units are feet. And then we have to estimate this S. Clear? This is the slope, and it will give us S minus S naught. And finally, we can arrive at delta X, that will be equal to E1 minus E2 divided by S minus S naught. So this will be in feet. So what we have to do is that these are now, the table continues, but now these are for the, you can see here this E1 minus E2, it will come here, the difference of these two. The difference of these two now we have to calculate, and then we have to calculate the difference of these two. So now the calculation continue, but now in the middle, average of the two. Now we are looking for average of the two. Clear? So what will be this E1 minus E2? This will be equal to minus 0.0221, minus 0.0221. From where it comes? This is E1, 4.2269 minus 4.2490. So this E1 minus E2, you will get this value here. Then for the average velocity, you have to do the average calculation. These are the two velocity. One is 8.889, one is 8.602. You take the average of the two. So the average of the two, that will be equal to here 8.746. This is equal to 8.746. Similarly, the average of the hydraulic radius. So this will be equal to 1.512. Now we have these average values. So you can calculate this S. We already discussed that this S will be given by this equation here. This is the equation. Now we have V bar, we have the Manning's N which is given, we have the RH bar. So we can now estimate the value of S, the energy gradient, slope of the energy line. So this S we can calculate, and this is equal to 0.00002874. Now we can easily calculate S minus S naught. S naught is here. This is your S naught. So we can easily calculate. This will be equal to 0.000874. And we can now calculate delta X. So delta X for this case, it will be equal to minus 25.286. Go to at least 3 digits after the decimal. So this is one row, and now next is for these two, 3.1 and 3.2. For this section, now we go for the middle, for the average V, for the average hydraulic radius, and the difference of the specific energy. Now we go for 3.1 and 3.2. In first case, we go for 3 and 3.1. Now we go for 3.1 and 3.2. So that's why we will have a second row now in the table. So this will be equal to minus E1 minus E2. That will be equal to minus 0.0292. Similarly, you calculate the average velocity. So 8.468. This will be equal to 8.468. Then you calculate the average hydraulic radius, 1.536. S we can estimate will be equal to 0.002638, and S minus S naught, that will be equal to 0.000638. And from here delta X, that comes out to be minus 45.768. So now what we have to do next is we take summation. This is what we said, that your delta X, that will be summation of delta X. So that will be equal to minus 71.054 feet. So now what the negative sign shows, that the section progress upstream. So negative sign means, it doesn't mean it is incorrect. So negative sign means that sections that we have taken, so it means that sections, they progress upstream. The sections, they progress upstream. This is important. So it means that the water depth decreases downstream. It means that the water depth decreases downstream. Clear? So this is what was asked, that you compute the distance to the section where the depth is this much. So we have a drawdown curve. Why? Because the sections progress upstream and the water depth decreases downstream. So it means water depth decreases downstream. We have a drawdown curve. Water depth decreases downstream. Decreases downstream. So essentially we have a drawdown curve. Now which curve here, that we can determine. As I said before, you can even determine that it is a drawdown curve. What we are getting from here is that it is a drawdown curve. It means that it is decreasing in the direction of flow. So we have a drawdown curve. Now which curve? We have essentially a drawdown curve. The depth is 3.2 to 3. This is, now we determine that it is essentially a drawdown curve. Which type of curve now? That we can also determine. How? As I said before, you calculate y naught. So in this equation, discharge is given. This is equal to 1.486 in the British gravitational system. 1.486 divided by n into A into RH, 2 by 3 into S naught, 1 by 2. Now you calculate y naught. From here you calculate y naught. Now y naught comes out to be how much? 3.5 feet. By trial and error. By trial and error you will solve this, and this comes out to be 3.5 feet. So now this is 3.5, and what is the depth range given? The depth range is given 3.2 and 3. So the depth range is 3.2 to 3. It is actually saying that the curve is like this, a drawdown curve. So it means that it moves from 3.2 feet to 3 feet. It is like this. Clear? 3.2 to 3 feet, a drawdown curve. So this y naught, it is 3.5. So it means that y naught, the normal depth, is above the 2. Let us calculate yc also, the critical depth that we can calculate. So yc will be equal to q square, as we already know, for a rectangular channel, q square divided by g into power 1 by 3. So what is yc? Yc is 2.806. 2.806 feet. Now you can see that this depth range, which is given 3.2 to 3, it is below y naught, but it is above yc. So it means that the given depth range, it is between the two. When it is between the two, we have type 2 profile. what we see is that YC, it is less than Y, which is given the depth range, and this is less than Y naught. Now Y naught is greater than YC. So what it means, we have a mild slope. This is what we studied in the previous example. YC is less than Y naught, so we have a mild slope. And now the given depth range is between the two, so type 2 profile. So we means that this is an M2 profile. So this is how we solve the gradually varied flow problems. Now we will take a break here and then we continue after the break.